Chapter 8, we're going to spend most of our time solving a single first-order equation, y prime equals f of x comma y with initial condition. We'll see in section 7 that all of the methods that we've studied for this single first-order equation work with very little change to solve systems of first-order equations, and we'll also see that second and third and higher order equations can be written as systems of first-order equations. So the methods we learn for this single first-order equation work for more general problems. First method we're going to look at it is, of course, Euler's method. Euler's method, you approximate the y prime by y of x plus h minus y of x over h. After all, the limit of that as h goes to 0 is the definition of y prime, so we just take a small h and plug that in for y prime, solve for y of x n plus 1, which is y xn plus h, and there's Euler's method. Now the error per step seems to be order h squared because Taylor's series says that y of x plus h is y of x plus h y prime plus h squared over 2 y double prime, so the error out here that we're neglecting is order h squared. But that's the error per step, and we're going to take n steps where n is proportional to 1 over h, b minus a over h, so we lose one power of h going from local error to global error. It's exactly like chapter 5 when we were approximating integrals, definite integrals. For example, trapezoid rule was order h cubed per strip, but the overall trapezoid composite rule, when you add them all up, you have n strips where n is b minus a over h. So the global error is only order h squared. So the global error is one order less than the local error, the same as chapter 5. And here, Euler's method, the local error is h squared, the order error per step. The overall error, which is what we're really interested in, is just should be order h. So now let's try it on a problem. We're going to solve problem 1f, y prime equals x cubed over y. Initial condition y of 0 equals 1. Here's the exact solution. That's a separable problem, pretty easy to solve. So f is x cubed over y. And here's our Euler's method program. It's really simple to program. Start with x equals 0, y equals 1, the initial condition, and every step x goes up by h, y goes up by h times f of xy, which is called yp for y prime, x cubed over y. So whatever your right-hand side of your differential equation, you just put it there, and that's all there is to it. Then we calculate the error at the final x value of 2. And we're actually going to run the whole thing 3 times with 3 different step sizes. Each time we'll double the number of steps. In other words, we'll cut h by a factor of 2 each time. And then let's see how the error goes down. If it's order h as we think, the error should go down by a factor of 2 every time we cut the step size by a factor of h. So let's try it. And the error with the first h is this. It is cut by a factor of 2 every time. In fact, there's almost exactly 2 the ratios. So that confirms that the global error of Euler's method appears to be order h. Now I'm going to splice in a part of a video from differential equations class, Math 2326, over Euler's method. We saw in the last section that a differential equation, first-order differential equation, y prime equals f of t and y, has a slope field. That is, at every point in the plane, at every point ty, if you calculate the right-hand side, f of t and y at that point, that tells you the slope of the solution if it goes through that point. And we saw that DE Tools has a tool that can basically follow the slope field. But you might wonder, how does the computer follow that slope field? The exact solution actually follows it exactly. That is, the Analytical solution is basically looking at those little arrows continuously and following them continuously, but even a computer can't do that continuously. How does it approximately follow the slope field? Well, it actually uses something more sophisticated than this, but let's pretend like it could use Euler's method, which basically Euler's method, it just looks down and, at the starting point and sees what the slope is at that point and follows that direction, but it doesn't pay any attention to the fact that the slopes are changing underneath its feet. It just follows the last time it looked down, follows that out a distance, certain time distance, let's say delta t equal to 1/100th of a second, say. So then every 100th of a second it looks down and says, okay, now here I am, what direction am I supposed to be going now? And then it goes another 100th of a second and looks down and says, okay, now what is the slope at this point pointing me? And it just follows it. And you can see that if you took a small enough step size, instead of every 100th of a second, every millionth of a second, that is every delta t equal to 1/1,000,000th of a second, it's going to get should be more and more accurate. That's basically Euler's method. You take a step size of delta t, and the smaller the delta t, the better, but the more work it takes. And every delta t, t increases by delta t, but f increases by delta t times the slope at the last point. In other words, getting from here to here, it looks and sees what is the slope field at this point and just follows that out there and doesn't care that the slope field is changing slightly underneath its feet. It just looks down and says, okay, now I'm at this point. Now which way do I go? And the slope field says go that way, so I go that way for another delta t seconds and keeps going. And you can imagine that the more often you look down, the more accurate your approximate solution will be. Well, the DE Tools also has a tool for doing that using Euler's method, so let's look at it. Let's look at it for problem 2. Problem 2 is y prime equals t minus y squared, y of 0 equals 1. That one is not separable and it's not even linear, so we won't be able to solve it ever in this class. I don't know if anybody can solve it, maybe they can, but it has a solution. And with DE Tools, you can plot the slope field and the computer can follow the slope field, and you can follow it by hand, but it's a lot of hand calculations. We'll do it with MATLAB also. But anyway, the differential equation is y prime equals t minus y squared, and you're starting at t equals 0, y equals 1. So this time we use the Euler's method app in DE Tools. And it won't let us just type any right-hand side we want to. We have to choose from a menu, but t minus y squared is one of the ones on the menu. So let's solve dy dt equals t minus y squared. And let's take a step size of 0.25. So we're going to take a step size of 1/4 of a second. There's the slope field. We're going to start at 1, 0. Now I could click on that point, but to get it more accurately, let's... okay, so we're starting at t equals 0, y equals 1. That was the initial point. And the slope at that is t minus y squared, 0 minus 1 squared, so it's minus 1. So the slope is minus 1. And so we go out to t equals 0.25, and we're going down with a constant slope of minus 1. Never mind that the slope underneath our feet is changing ever so slightly. And we get to the 0.75 because we're going down at a rate of minus 1, and we go out 0.25, so we get down 0.25. Now we just click on that and do another step. And now the slope field at the new point is not quite as negative. It's still negative, but not as negative, so we don't go down as much the next step. And then we take one more step and one more step. Now it's actually going up slightly, very slightly. The slope is almost 0 there, so it goes up very slightly, almost level. And then one more step, 0.25, and we end up with basically 0.75 again. So now if you want more accuracy, you just take a smaller step size. We start all over with Euler with, let's take 8 steps of 1/8 each. And start at the same point. Now we take 8 steps each time we look down. Where are the arrows pointing now? Don't pay any attention to the arrows until you've gone 1/8 of a second, and then you look down and say, now which way do I go? Take 8 steps. And we end up with 0.80. Now, I don't know the exact solution, nobody does, so I presume that's more accurate, but we don't know the exact solution, so we can't be sure. But remember, with the step size of 0.25, for 1/4, 4 steps of 0.25, we ended up with 0.75. Now let's do the calculations by hand and compare. So here's the same problem, y prime equals t minus y squared, y of 0 equals 1. We're going to take 4 steps of 0.25, which is exactly what we did with the DE Tools app. But we're going to actually show the calculations now. So we start at t equals 0, y equals 1. F of t, the slope at that point, is t minus y squared. Whatever t is, whatever y squared is. T is 0, y is 1, so this is 0 minus 1 squared. Slope is minus 1. And so y goes down with a slope of minus 1. We go out 0.25, it means it goes down minus 1 times 0.25 down to 0.75. So the next time we look down, t is 1/4 and y is down to 0.75. What's the slope field there? Well, it's t, which is 0.25 now, minus y, which is 0.75 squared, and that gives minus 0.3125. So it's still going down, but not as fast. The new y is the old y, 0.75, plus h times the new slope, 0.672, so it goes down some more. Then we look down again, and now t is 0.5, y is 0.672, and t minus y squared is 0.0486, which is barely positive. So now it's going to start going up just a little bit, and it goes up to 0.684. Take one more step. Now the slope is a little more positive, 0.282, and it goes up to 0.754, which is to 2 significant digits, the same thing that DE Tools told us. Well, this is obviously not something you want to do by hand, but we can easily automate this and do it with MATLAB, so let's do that. Same problem again, but this time with MATLAB. So here's a MATLAB program that does exactly what we did by hand. Start out with t equals 0, y equals to 1, and take 4 steps of 0.25 each. Each step t goes up by h, and y goes up by h times f, where f is t minus y squared. And we print out t and y and plot it. Plot the solution. And there's the solution. Take 4 steps of 0.25. T goes up by 0.25 each time. Y changes exactly like we calculated by hand and with the DE Tools, 0.7545. There's the solution plotted. Now I'm going to run it again, but instead of 4 steps of 0.25, I'm going to take 40 steps of 0.025. And this is the new solution. Now it's looking down every 0.025 seconds. And presumably this is more accurate, though we don't know the exact solution, so we can't be sure. And now let's take a problem number 15 where we do know the exact solution. So problem 15 is y prime equals the square root of y. That's autonomous, so it's separable and it's pretty easy to solve. And so we can compare the exact solution, y of 0 equals 1 as the initial condition. So let's do that with MATLAB. Now let's solve problem 15, which is y prime equals square root of y, y of 0 equals 1. That is autonomous and therefore separable, so we can actually solve it. And the exact solution is y equals 1/2 t plus 1 quantity squared. And let's first take 4 steps of h equal to 1. And the error at the last point, since we know the exact solution is 1.44, that's the difference between this and this. So we took 4 steps of 1 each, and the solid line is the exact solution, 1/2 t plus 1 quantity squared, and this is the Euler method solution. Now if we, instead of taking 4 steps of 1 each, let's take 40 steps of 0.1 each, and we should get a lot smaller error. So with the smaller step size, we get an error of 0.16, about 10 times smaller. And now you can see the solution is much better. The solid line is still the exact solution. But now Euler's method is looking down every 0.1 seconds, so it's following the slope field more accurately than it did with h equal to 1.